So this is the Dask tutorial. I will give you a quick intro to what Dask is and how you can use it. Is here anyone who is familiar with what Dask is, has already used it, or okay, a couple? Are people here familiar with like pandas? NumPy, scikit-learn. Dask integrates with all of these libraries. We will today look at how you can scale a panda project with Dask, and also how you can run arbitrary Python code in parallel through Dask, either on a local machine or on a distributed system. So a little bit about me. I work at Coil, where we deploy Dask for people in the cloud. I have a background in mathematics. I worked in the open source space for quite some time now. I'm a pandas maintainer for close to 4 years now. And since I work at Coil, I'm also a Dask maintainer. My main focus is making Dask data frames faster at the moment. This is something I'll talk about Friday, if you're interested. What we will look at today, I give a quick intro, like 10 to 15 minutes, what Dask is. Then we will work on Dask clusters. In the beginning, we will work on a local cluster that only runs on a single machine. And then we will scale out to a distributed cluster that runs in the cloud and do some heavy data frame processing. And we will have a Q&A in the end. But really, if you have any questions, just raise your hand and I'll try to answer them on the spot. We don't have to wait till the end if you have anything that you want to know more about. We will do some exercises later on, but we'll get to how we can set this up in a little bit. Anyone here that has an idea why he wants to learn more about Dask? We have workflows that will benefit from Dask, or basically anything, just want to learn a new tool?
Just learning how to parallelize my code, make it faster in terms of just sit around waiting. And I think that would be more efficient learning how to do something a little bit more.
Perfect. That's what Dask is good at. Anyone familiar with one of these three things? Your code is too slow. Your data doesn't fit into memory. That's another common problem. Or maybe both. That's a nice diagram where Dask is useful. If you're in the bottom left corner, you have an acceptable runtime and your stuff fits into memory, then you should bother with Dask. But it either takes too long, or you have memory errors, or both of them, then Dask is very helpful, or can be very helpful. Depends on the use case a little bit. We will today focus on the upper left and the down right, and then combine both of them together. If your workflow is, for example, pandas or NumPy based and it runs in a second or a half a second, then don't bother with Dask. That's not where Dask is useful. There's too much overhead in a distributed way that this would be beneficial to users. But if your workflow runs for hours, or your data frame or arrays don't fit into memory, then Dask is a tool that can help you. So what is Dask? Dask brings the power of parallel computing to the PyData ecosystem. Historically, Dask was built around NumPy and pandas. Dask itself was founded almost 10 years ago now. Initially, the first APIs were Dask Array, which parallelizes NumPy calculations, and Dask Data Frame, which is the same but for pandas. But pretty quickly, power users were building their own weird ways of misusing the public API. So what was done back then is Dask provided a new API that allowed for lower level parallelism. Generally, the goal is do more work in less time. That's what parallelizing is for. Generally, Python is a very powerful language, especially through all the third-party integrations, third-party libraries like NumPy, pandas, scikit-learn, PyTorch, TensorFlow. But most of them don't scale very well naturally. They were implemented for single machine usage. Lots of people use Python, but if you reach the boundary of a single machine, then you need other tools than what you would normally do. And that's where Dask or also something like Spark normally comes in. The Dask data frame API, for example, wraps the pandas API. And most of the things that you would do in pandas are very similar in Dask. Obviously, it's not a one-to-one switch because distributed computing is very different from computing on a single node. But at least the APIs will feel familiar from all the integrations that Dask built. Before we get going with our notebooks, we will look a bit more deeply into how Dask scales pandas, just to give you an idea how the distributed model in Dask works. I might be a bit biased. As I said, I'm a pandas maintainer, but pandas is great if you work on small and medium-sized data sets. Like as soon as your data sets grow, then the single core functionality of pandas will reach its limits at some point. Like if you have a data set that has 10 gigabytes of Parquet files, then pandas is probably not the right tool at the moment, because you would ideally like to process this on more than one core on your machine. Most notebooks today have at least 4, 8, 12 cores, so only using one is not the most efficient. Thank you. That's where Dask comes in. It's basically the same car, but we plug in a different engine. The API is very, very similar. We will see this later. Like most of the things that you can do in pandas are very, very similar in Dask. But we lose the limit on data size and on processing power. Dask really can run on huge single machines and utilize all the cores, but it can also scale out to hundreds of machines in the cloud. There's not really a limit on data size anymore. That's Dask data frame. As I said, what pandas does is it uses one core, and Dask comes in and uses all of your cores. And it triggers pandas computations on each and every one of the cores that are available. If you want to scale out, then Dask just does the same but on multiple machines. Dask is aware of all the workers in your system, and it pitches the pandas computations onto all of your machines. A Dask data frame by nature is like a collection of pandas data frames. If you have a Dask data frame with 100 gigabytes of memory, chances are that you have like between 500 and 1,000 small data frames. Dask just orchestrates all these pandas data frames and brings the computations together. We don't implement new stuff in Dask except for a small subset of the API that's different in a distributed way. But if you would use a sum, then what Dask does, it computes a sum on every one of the pandas data frames. Then it squashes the results together and sums them up again. So there's no custom implementation for Dask. We dispatch for most of the things to pandas and just handle the orchestration. Things like merging work different in a distributed system, because if you merge two data frames, like the value on the left might be on machine 1 and the corresponding value on the right might be on machine 50. So we have to push the data through the network to get them to the same machine. So these are areas where we implement custom stuff. So what we'll do now, we need a notebook to run the materials for the tutorial. We will use Coil for this. Historically, Coil spins up Dask clusters, but we can also use it to create a notebook with a Docker image that has all the materials available, so you don't have to install anything for this locally. The only thing that you have to do is pip install Coil in any Python environment. You can also do conda or mamba install, doesn't really matter. It's a Python-only library, so there's no compiled stuff in there. And then we come to the next two steps. Would be great if you could run through that real quick, and then we continue. Any questions, just raise your hand.
Is there a preferred version of Python?
Sorry?
Is there a preferred version of Python?
Anything above 3.8 is fine. Doesn't matter. The COID login and the COID notebook start is something we got to later. You don't have to type that code.
So we just install it.
Installing, and then we'll jump over to the GitHub repository where you can copy and paste the remaining steps. Does anyone need a little bit more time? Everyone who is finished with installing Coil, you can move over to this link, Dask -NYC. And that's a GitHub repository, and scroll down to the README file. So what we're doing now is we're logging into Coil. I pre-generated a token under my account, so you will all log in as me. And then we can use that to spin up resources that we can use for the Dask exploration. You can just copy-paste the statement into the terminal where you installed Coil. And then it should take a couple of seconds, and then there's a screen of authentication successful. Should look something like this. Nathan and David will help you if you run into any problems. And when you copy paste this command, can you add minus minus dash dash account and then Dask dash tutorial? Doesn't really work, sorry. Only the part in the second line here is what you have to add. Does this work?
It's something.
Okay, then. This will take like between 1 and 2 minutes until the instance is up.
Stuck at login.
Okay, David. When you see that the notebook is starting up, that's what the widget is telling you. Then it will take between 1 and 2 minutes, and then they will open a tab in your default browser to bring you to the Jupyter notebook.
You still have the same area. Same thing. Okay, let me just go ahead and check it. So if you're getting a network error, we're looking into it right now, and we'll get that.
I think they figured out over here.
Okay.
On the Git readme, there is no account thing, so if you're copying, you have to add that account.
Did the double dash
That will do it.
Yeah, that worked for me after they did the internal network
Thanks.
error.
Thank
Well, thank you. I just had a lot.
Yeah. Okay, good. So what?
Sorry. I can send you the, but there seems to be some error in my config.
So let's take a look at your config now. Have you installed Dask before?
No.
Okay, it's interesting. Just try to install Chrome again. Did you already do the second one? That one, I think, okay, properly?
Yeah.
Let's try that one. So the second one? Okay. So you can do that with the second? No. Yeah. I just want to start. Thank you. It's hard getting this 50 people. Okay, so I guess he's in first. Okay, I'm gonna ask you. What's up? So we got a config issue.
Yeah.
Um,
I don't see that.
did you all get to the tab that's showing the Jupyter notebook?
But if he's
My notebook's booting now. There's a folder that's called notebooks.
You know what?
And then there is 00 test drive. You can all open up that notebook and just run through the cells. If you go from top to bottom, then they should all work very well. I give you like 2 or 3 minutes for that before I run through them and explain you what happens there, just that you can get a little bit of a feel for how Dask works.
SSL error.
Is your notebook open?
No, at the terminal error.
He's like, copy, when he's trying to log in.
You can go back to SSL error. Outside of this folder? Yeah. No. Virtual environment. Or else I would be in the original. But it wouldn't know what it is.
Okay, so he's. Lovely job. I remember. What it's supposed to be. Okay, this is exactly what you should see. So this is long. Let me know.
Oh.
So you should all have this tab that's showing the Jupyter notebook. The tutorial materials are all in there. And now we'll just go like briefly through the test drive notebook. It's a very, very brief intro to Dask on a local machine before we move over to like scaling a bit more aggressively. So we will start with Dask data frames. Generally, Dask has like many extensions. There's Dask array, Dask data frame, a couple of other things. By convention, we import this as DD. Like someone decided that all of our data science libraries are two-letter imports. And then we prep. We download the files real quick. The notebook is spin up in the cloud, so network connection is fine. These are a couple of gigabytes. If you would load this with pandas, then we would get out of memory errors. That's why we moved to Dask here. And what we can see here is instead of pd.readcsv, we just do a dd for Dask data frame.readcsv. Command is very similar. We specify a couple of our D types, and now Dask didn't actually do anything. Dask is lazy, so it's just registered our intent to read a CSV file, and now we can do a head to get some data. Up until now, this was exactly the same API that we would have used for pandas. The statements are syntactically exactly the same. Since Dask is lazy, we have to tell Dask at some point that we want to trigger a computation. We will go into more detail later on. Head is just an exception to that rule. But if we want to do a group by here, then we use pandas syntax up until the mean. Sorry for that. And then we tell Dask with compute that now we want to see what's going on here. And this will take a little bit. As I said, it's a couple of gigabytes. If you would have done this with pandas, this would have run for 30 to 40 seconds on a bigger machine. But Dask uses all of our cores, and so it's relatively quick. We briefly look at like our data frame. If you would do this in pandas, then you would get the data. Dask is just telling you that you have these columns. These columns have these data types, but Dask actually doesn't know yet which data are in these columns. It just knows how they will look later on. This is what Dask registers. Like, we call this the task graph. It's the execution plan that we will execute later on. Like, we start with a read CSV, then we will convert to PyArray this is internal detail, and then we will get our result back. We have like 9 different CSV files. That's why you have 9 different execution strings here. Dask array is a NumPy extension. Dask data frame wraps the pandas API pretty closely. The differences for arrays are even smaller than they are for data frames because arrays scale a little bit better over multiple machines than data frames do. So we create a random array. And what we can tell Dask is that we want each of our NumPy arrays inside of our huge Dask array to have like 1,000 rows and 1,000 columns. And this is what we end up getting. We can also like modify this and tell it like we want 2,000 rows. Then this will look a little bit different. They are not squares anymore. They are a bit longer than they are wide now. We call this chunks. Like one chunk is one NumPy array. And then we can get back to our syntax, NumPy syntax. Like we select 10 rows and 5 columns. And again, nothing happened here. We have to trigger an explicit compute to actually get any results. But as soon as we do this, we get back a NumPy array that we can do NumPy calculations on. Compute moves from the Dask array world that is lazy back to the NumPy world that is eager. as we can see, we had a pretty huge array, but Dask was able to sum this up relatively quickly. In the interest of time, I will skip the delay part. We will look into futures in a little bit, which is a very similar API.
Sorry, Karen?
Yes, sure.
Try to do the shape of the document. The first shape like delay something.
Mm-hmm.
So you cannot really do the shape of the document.
In here? Or?
Out of the document before.
Okay, you did df.shape.
Yeah.
Like, this is lazy. It doesn't actually trigger any computation. If you want to, like, get a result here, then you would have to do compute. Yes, which then will, like, Dask doesn't know how long your data frame is. It knows how many columns you have, but it doesn't know the length. And the length requires a computation. So if you would do, like, len df, then we'll get back the number of rows. But this is actually a little bit more expensive because it has to look at the data and read them from disk and then store them in memory on your machine and then compute the length for every one of the chunks. Any other questions so far? Before we look into some more like hands-on results, I give a brief overview of how Dask works from an infrastructure point of view. If you tell Dask that you want to compute anything on your array, data frame, or any other Dask structure, then it just creates a collection, which is a Dask data frame, a Dask scalar, a Dask series. Before we execute this, we have to create a task graph, which is an execution plan, basically. It creates the order in which you have to execute, in which Dask has to execute all the operations. For example, if you read from storage, then do a group by and then a sum. The task graph will encode this knowledge that you first have to read from storage before you can do your group by, and then you can calculate your sum. It wouldn't work the other round. That's what the task graph is. Dask can run in many different environments. Like, you can pip install Dask on your local machine and run it there without doing any specific setup. But the more common usage is that we use a distributed scheduler that schedules these tasks on many, many, many different machines. For example, a 20 worker cluster in the cloud, which is something we'll spin up a little bit later. The distributed scheduler here is the one that's firstly the most complicated scheduler, but it's also the scheduler that is the most optimized because that's the more common use case. And running it on a single machine is relatively simple compared to executing it in a distributed environment. Some quick terminology. A Dask client, that's normally your laptop or wherever you run Dask from. In this tutorial will be the notebook. Then there's the scheduler that's actually running on your cluster. It's not running on your notebook, so there's network communication between the client and the scheduler. And the scheduler, again, is aware of how many workers your cluster has. If your cluster has 100 workers, they are all registered at the scheduler. Scheduler and workers normally run in the same network. So they will both run at AWS or at one of your local data centers. And the client connects to them. If you look like this if you look at building a barn, this is a bit similar. Like, you have a lot of workers that do the actual work, like building the walls, the roof, whatever. And then you have the Dask scheduler, which keeps all of the control. Like, he tells the workers to do this task and then the other workers to do something else. Our graph is more or less like our plan, how we want to execute our things. This is what the scheduler uses as a baseline to make decisions. And then there are a bunch of Python libraries that integrate with Dask, that do the actual computations, the heavy lifting. this brings back, like, when to use Dask brings back our diagram from the beginning. If you have acceptable runtime, then you don't have to worry about Dask. But if you run into, like, either performance issues or memory issues, then you can switch over to Dask and give it a shot to speed up your stuff. What we generally suggest users is that they shouldn't use Dask if they don't have to. Like, distributed computing brings in a lot of heavy stuff, and if your computations run fine on a single node, then you shouldn't have to worry about this. This is a bit similar to like Spark usage, for example. If you have a small, tiny pandas data frame, you wouldn't move to Spark because setup is like a pain, and you don't want to deal with that. And the notebook also contains a couple of links to Dask documentation and blog posts that give a deeper insight into these concepts and how you can get started. Let's now move over to the futures notebook, which is the second one, 02. And when you're there, you can execute the first cell. We will need that later for some exercises. This cell will spin up a local Dask cluster that is only running on this machine. So there's no network communication going on. The client and the cluster are on the same instance. This is helpful if you want to parallelize some things, but your resources generally on this machine are sufficient. For example, if you have a huge machine somewhere in the basement that has a terabyte of RAM, you might not want to switch over to the cloud because that just brings additional complexity. Like if your data fits in there, you can use a local cluster that runs only on this machine. Dask comes with a dashboard that shows you what's going on your cluster. This is on the left here, the Dask logo. If you open up this tab and press the search icon, then it will connect you to your Dask cluster. These are all the different diagnostic tools that Dask provides. Generally, in the beginning, it makes sense to look at the task stream, which is in the bottom third. And we can open that one up, and the progress, which is a bit above that. This is also something that's interesting to look at. When you found these two, we can just arrange them on the right of our notebook so that we can still see our code. And just by pulling them over. We will now look into Dask futures. Dask futures are built on, are designed like the futures library from the Python standard library. The API is more or less the same, but they are a bit like multiprocessing on steroids. So you can either scale them on your local machine or you can scale them out distributed in the cloud. And Dask handles all the orchestration for you. A typical workflow that we see is that users process a bunch of files and want to do this in parallel. Every file does the transformation, and then you write the results somewhere, like in a database, S3, local storage, something like that. This is where futures are very helpful. If your computation is unstructured and it doesn't fit into the data frame world or into the array world or into any other libraries, then you just want to write plain Python code. This is where futures are helpful. What we do is we have three very trivial functions: increment, decrement, and add. We could run all of these three sequentially without using Dask at all. But we added a random sleep so that it takes a bit longer and we can see more. So the computation works perfectly fine. But we can also submit it to our Dask cluster. And then we see something happening over here. We told Dask that we want to do one computation. This was registered on the scheduler. And the scheduler then distributes this to our workers. The future itself client.submit tells the scheduler that we want to execute this, but it doesn't block on the computation. So if your computation would run for hours, the Python session would still return immediately back to you. And the future status is pending. So it's like it's like on a scheduler and it will get scheduled soon. So since this is a very short computation, if we look at the future again, then we will get status finished. That means that our computation is done. And future result, we can use future result to look at whatever we computed there. We can also submit multiple things at once. Like client.submit can be used on any random function. We now submit 2 increments and then we sum them up. And then we will be able to see on the right how these will get executed. So we had 2 increments up here, and then the sum, which is down here. So Dask took care of that for us, of the scheduling for us, and returned whatever we computed back to our machine. Now we have a quick exercise. The previous functions that we had, like increment and decrement, we can do this in a loop sequentially. And basically 10 times, but this will take a little bit because every one of these calls sleeps, and so we will roughly spend 10 seconds in that loop. 9.3 seconds. This is a workflow that can get parallelized pretty easily. So there's no need that we have to do this sequentially because the results don't depend on each other between the different iterations. So we can use Dask to parallelize the work. So what you can do is basically copy this code statement and then use client.submit. Analogous to what we did up here. To distribute, to register this work on the scheduler. I would give you 2 minutes to play around a little bit and then we can go through this together. So the changes we have to make to our for loop are pretty small. We add a client.submit to both lines. And then we tell Dask we want to use the function increment and hand over the argument x. We can do the same thing for decrement, the decrement function, and we want to hand over the previous result of the first iteration. Dask will figure this out automatically for you, that the second line depends on the first line for every loop. And then we can run all of this. If you want the results back, you can do client.gather and put in all the futures that we created. Yep, thank you. Then we can see how Dask utilizes all of our cores. I gave him 8 different workers, and we executed stuff on all of them. Obviously, 10 iterations aren't that many. If we scale this out to 100, then we will be able to see a little bit better what's going on here. Dask just uses all of its workers and schedules the computations sequentially on every one of these cores. That means if you would have 50 workers, we could do this way faster than we can do it with 8. So this would scale out pretty linearly to a bigger machine. Can also do 500. We can increase this as much as we want. Generally, this is a helpful API if you want to do anything in Python that doesn't fit into any libraries. If you can do something easily with a data frame, then you shouldn't bother with any of the low-level stuff, because that would just cause more work. This will run a little bit, but we will move over to the data frame notebook. This is number 3. Before I, yes?
How did you determine what a reasonable number of workers was initially?
We booted them on a machines with 4 cores, so I just said I want 8 then. So that's it a little bit better. By default, Dask will create 1 worker per core if you do a local cluster. So you would have gotten 4 workers, but that was a little bit too low for them.
So you probably would want to do 16.
If you do serious processing, not increment and decrement, then that's too much. It would lead to oversubscription on your resources and slow you down. Normally the default is pretty sensible. Before we get started with the Dask data frame stuff, I would like to ask you to execute this line here. That will spin our cluster at AWS, but this will take around 2 minutes, so we can go over the theory while we are waiting. Just execute that cell and then it will do its thing. As we briefly looked at earlier, a Dask data frame is basically parallelized pandas. Pandas is single core, Dask is multi-core, and also multiple machines. So we can process a lot more data than pandas can in efficient time. On the other side, it's not. I wouldn't recommend using Dask if your data frame only has a couple million rows. Then pandas should be totally fine. You would move to Dask when pandas isn't sufficient anymore. It's too slow, too much memory, whatever. Wes McKinney, he's the pandas founder, once said you should have 5 to 10 times as much RAM as the size of your data set. If you use pandas, that's not totally true anymore. We did a lot of memory optimizations that reduced the memory footprint of pandas since 2.0, but still, if you don't have 3 times as much memory as you have data, then you will still run into problems. 5 is probably a sensible default at this point. My cluster now has arrived. So if you move over to the Dask logo on the left again and refresh your Dask cluster, then we will connect to the distributed cluster that is in the cloud. Just press the search icon and then it will refresh all the dashboards that you might have opened earlier. we will look at the New York City Uber and Lyft rides data set. That's a data set that tracks all the Uber and Lyft ride shares that happen in New York City. It has around 100 gigabytes in memory, so that wouldn't be a sensible, pandas wouldn't be a sensible solution for that problem. But Dask can handle this easily. This is on the smaller size of data sets that you can process with Dask. I forgot to import Dask data frame. As I said earlier, by convention we use DD. You can use basically any short form, but this is what all the documentation and Stack Overflow and whatever uses. Yes?
I'm getting client errors.
Yes?
I just had a quick question regarding Dask or data frame. Could you throw some light on like what's the difference between Dask or data frame and Apache Spark or MapReduce like for data manipulation?
Spark is very, very good at MapReduce. If your paradigm fits in there, then Spark is probably a sensible choice because it does a lot of query planning. We are building this into Dask now, and then we will get up to speed there. But if you need more flexibility, then like Dask is a better choice. Dask uses most of the pandas APIs, so if there are things that you can do in pandas that you can't do in Spark, like there are lots of things, then Dask is probably a better choice for that. Does that answer your question? But if you just do group by and then a sum, then Spark is very good at that.
How does Dask do dependency management for like model workers?
This depends. Coiled handles this for you if you use a managed service. But if you do this yourself, for example with Kubernetes, then you would have to install all the same Python environment on all your workers. So this is not handled by Dask out of the box. Dask relies on having the same environment on the scheduler, worker, and on your local machine.
I've been using Arrow on my local machine. I have a very bigger machine, so I don't do distributed. Is there still, should I be motivated to move Dask, or, I mean, what works now is fine, but why would I pick this over Arrow?
So you're using Arrow only without any libraries to build on top of Arrow, is that correct?
Right now I use like the R's API to Arrow, so I use R, and things work fine because I can sort of lazily build my query and execute at the end, right? I'm moving that from R to Python. What should I do? Should I pick that?
Not every part of Arrow is, in Python, not every part of Arrow is multi-threaded. So if you do a sum over a huge array, this will still be single-threaded. While Dask would split this up in chunks and then do these chunks in parallel. But if your workflow works fine with Arrow, because the multi-threading is available for whatever you do, then stick with Arrow. Personally, I don't like working with Arrow. It's too strict for me. Like Pandas is an Arrow backend these days, and we pitch over a lot of these problems for users. But like this is personal choice. And now we have our data frame. These are Parquet files. They are stored on S3, so we have to download them to our cluster. Like network speed in the cloud is pretty fast, but it's still not an instant operation. So we start with computing the length of our data frame. And now we will see on the right side that we have 720 different Parquet files, and Dask is like reading all of them and computing the length. It's like, I don't know, 783 million rows, sorry. This would have taken forever if you use something that's only single node. But Dask was able to do this like in a couple of seconds. We can also look a little bit at our data and compute the head. The head looks only at the first file because we know that the first like n rows are in there. So this is pretty fast. We don't have to look at all of them. And then we get back a pandas data frame that contains the first 5 rows of our data set. This is generally helpful if you want to have an idea what's in your data set, but not to do any actual computations, obviously. Dask grabs the pandas API pretty closely. So if we want to compute the max of the driver pay, like this is the amount that is paid to your Uber driver from Uber itself, not the amount that your ride costs, then we can use exactly the pandas API and trigger a compute in the end. This again reads the data set from S3 and then computes the max. So the maximum fare was like around $5,000. I don't know where this person went, but it must have been a long ride. Since Dask is lazy, it won't cache intermediate results, which can be a bit annoying if you repeatedly want to access the same data source. There is a thing that's called persist that will load your data into memory. And then all these data will be available on your cluster. So you don't have to repeatedly access S3, which means that computations afterwards will be very good, since there's no I/O stuff, no network stuff. You already have all your pandas data frames in memory. So if you do something like length now, this is very, very fast. There's no like S3 stuff anymore. It's just like it asks all the 720 pandas data frames what their length is and then aggregates the results together. ddf.columns is exactly the same as a df.columns of the pandas data frame. It shows you the index of your columns, which is helpful if you want to do aggregations or stuff like that, or just want to see how your example looks like. And now I have a couple of short exercises. I would give you 5 minutes for that, just to play a little bit around with the cluster. All of these queries have the pandas syntax and then a dot compute at the end. It's pretty closely aligned with the pandas API. For folks who got a permission error, could you try adding this line to the read parquet call?
Make that bigger, Patrick. Make that bigger.
Yeah, thank you.
Sorry. Yes.
I have a question. So you mentioned about a function persist which brings the data in memory. So if we don't do that, then are all the operations happening over the network?
If you don't do that, then if you compute a sum over one column, it will read from S3 and then do the sum computation. If your next cell is doing a minimum computation on the same column, it will again read from S3 and then do the minimum computation.
Will it be slow in that case?
If your data set is large, yes.
So then if we bring all the data in memory, will that not cause a memory issue?
And the data is scattered over your cluster. So if each of your machines has like 16 gigabytes and you have 20 of them, then you have 320 gigabytes of memory available. The data set only has like 100 gigabytes. So Dask will distribute the 100 gigabyte evenly across your workers. And then every worker will have like 5 gigabytes of memory. We can look at this here. Like each and every one of these workers holds around 5 gigabytes. And since every worker has 16 gigabytes, we are fine. This will obviously be problematic if your data set is like 1 terabyte and you have like 300 gigabytes of memory available. Then this option is not possible. Then you would have to read from S3 repeatedly.
But workers are really over the network, right?
Yes, but if you do like on the data frame a sum computation, then every worker will have one row to send over the network. And that's like a couple of kilobytes. That's pretty cheap.
So Dask is basically distributing the workload.
Yes. I will go briefly through the first couple of examples before we wrap up for questions. We only have like 6 minutes left. How many rows are in our data set is the same as we've seen before, like it's just a length computation. This is a bit more interesting. There's a column tips, which represents the amount that was given as a tip to every writer. And we can find out how many writes were tipped in total. We use the pandas syntax here. We select the column tips and filter for tips being greater than 0. I have a typo there. And then we can do a length computation on that one. Like 124 million, so that's roughly, that's not that much. I would have expected more. We can also find out, like, with a group by, how many writes are operated by one single operator. This again is like pandas syntax, and then we use this column which specifies the operator that operated that write. And then we get a lot of groups, and we basically want to get the size of each and one of these groups. And then we again have to trigger compute. I'm sorry, to these. This now executes the group by in parallel. We group every chunk, compute the size, and then again we pull all the data together and do the aggregation before we return to our client. You can see this one in the documentation. It's not in here, that's Uber. So Uber operated by far the most writes. And this one's Slip, which is roughly 40% of that. And the other ones are smaller ones that I don't know. I added a notebook in the solutions folder that shows potential solutions to all of these queries if you're interested. And now we can stop for a couple of questions. Are there any? Yes.
I'm curious, if I have a data frame that fits in what I want to do, like sometimes I need to do calculations on chunks of it, so I'll do like a group by, and maybe I'll use Java to do the calculations on each segment as well. Is it going to be faster to do something with Dask, or is it going to be about the same, or?
It depends how good your current solution parallelizes.
Okay.
Like Dask will split stuff to all of your cores. So if you can't do that at the moment, then Dask will most certainly be faster.
Okay.
But if your current solution also does this, then it's probably not that big of a difference. But if your data fits into memory, it's more like using all the cores to make your computations go faster.
Yeah. Okay.
Any other questions? Like anything, not only to data frames. I think it's running till 12:10, is that correct? Or oh no, we started at 10:50, so we still have 20 minutes left. Sorry for that. Then we can go through the other examples and move over to some custom code that you can run with Dask data frame, which is maybe a bit related to this question. So this is a precursor for one of the next questions. We want to find out the average driver pay, which is just a simple mean computation. A mean is hard in a distributed way because if you calculate the mean over every chunk, then you will only get a subset of that, and then if you compute the mean over all chunks, you would have to account for the differences in length, for example. So what Dask does, it splits this computation up into a sum, which sums up all your chunks, and then a count, which counts the rows. And then we'll get back the actual mean computation. We will be able to see this in a little bit down here. Sorry, that's muscle memory. Let's repeat that. We have a count here and a sum here, again, which then is aggregated into a mean computation. This is one of the things that differentiates single node computing from distributed computing. Some things are just hard in a distributed way. If you ask pandas for the median of your column, this is very easy. It just looks at all the values and then gives you back the median value in there. But if you ask Dask for the median, this gets significantly harder because it doesn't know how your column is ordered. The median actually might be the smallest value in the first chunk, and not the median value in the first chunk. So some things are not part of the Dask API. We offer an approximate median calculation that approximates the median, but it will probably not be the exact value. There are some algorithms to simplify that. This is just something people have to account for when they move from a single node computing to distributed computing. Some things are just more difficult and not as easy.
How does this handle building model approximating say weights and a regression or parameters? How would you fit because if you fit it in one chunk, it will give you a different answer than just using all of them.
We dispatched the scikit-learn for that. Dask has an DaskML, that's a sub-library that wraps scikit-learn, but I'm not maintaining that. But the solution is, this is the sole problem. But yeah, just generally some things you just can't do in a distributed environment. Sometimes there is no solution for a problem. At least not a solution that's very expensive. We can take a brief look at something that's very, very annoying. If you want to drop all duplicates from driver pay, it's like a float, so there won't be that many duplicates in there, probably. If you just do a drop duplicates on this column, this will be a very, very hard problem for Dask. What we do now is let's look at the worker memory, so that we can see a little bit what's going on here. And we will first start with dropping the duplicates for every chunk. That shouldn't have been that fun. Functions. Maybe there aren't actually that many rows in there. Now let's use another column and let's drop out date time, which is more likely to be unique. What Dask is doing, it drops all duplicates on every chunk, which is fast. It's basically a pandas operation. But then it will pull all the remaining values onto one worker, which obviously is not great, as we can see here. The memory on this worker continues to grow, and in a little bit we will probably reach the red area, and then this computation is killed by Dask itself, because the worker would run out of memory. This is one of the problems that we are currently working on a more efficient solution. There are more efficient ways available, but it's just like hard doing this efficiently on multiple machines, as long as you don't know that a given value is unique. And what we can see here is like Dask runs into the red space, and then it will restart the computation because it thinks it can do better. This happens like 3 or 4 times until it says that won't work out. Another thing that is different between pandas and Dask, like pandas data have to fit into memory. Dask can spill to the disk that's attached to your workers. Meaning if I go to this, what you can see here is like it's the bottom line. In this pop-up window, it's built 2 gigabytes of data to disk. That is how it was able to accomplish this computation. Like pandas would have just arrowed with like out of memory. That said, if you use the disk, that's very, very slow. Like writing to disk is not the fastest thing you can do compared to memory computation. So it will probably help your computations to succeed, but you will pay a hefty price with respect to performance. What we can see up here is like the last aggregation of drop duplicates took 35 seconds, while all the block-wise drop duplicates operations, they are in here, they only took like 200 milliseconds. So the network transfer here really slowed us down. Something that's generally interesting is like Uber takes a cut of the earnings of the drivers and like finding out how much that is. Sorry. It's something that's pretty interesting. This will also explain why Uber isn't making that much money. So we use the driver pay and you divide by the column base passenger pair. And then trigger a compute. Like both of these operations don't actually do anything. They just tell us that we want to get a sum and another sum, and then we want to divide both of them. But if we remove the compute briefly, then we'll just know we get a scalar back, because 2 scalars divided by each other are again a scalar, but not what the actual value is. This is what compute does for us. And we can see that like Uber pays its drivers around, Uber and Lyft pay its drivers around 81%, which is more than I expected, to be honest. So the charge on the app isn't that high, which explains why they're burning a lot of time. Something else like what was I'm from Germany. We tipped most of our cab riders. I was a bit curious to find out if this is true for the US as well. We can again use the license of the operator to group over. Firstly, we have to define how many rides actually get tipped. We can do this through getting all tips that are not equal to 0. Like through assigning a new column. And then use that new column to calculate the mean. is a bit more expensive because we have multiple operations that have to happen after each other. Like first we assign a new column before we actually do the group by operation. And what we can see is like the number here is the percentage of what writes were took. You can see that like it's only 15 to 20%, which is like a lot lower than I expected. I don't know how you feel about that. But again, up until here, everything of this is like pandas syntax. And then we just tell Dask that we want to compute. For most of the things, the switch from pandas to Dask should be pretty straightforward. The last topic that I wanted to talk about, at least briefly, pandas has things like apply or map or aggregate or transform, where you can execute anything you want. Doing an apply in Dask is a bit different because if you apply to every chunk, then you don't have a guarantee that your apply works as you would expect it, because like the values you would need for that specific function might be in a completely different chunk and you can't combine them. So apply in general triggers a shuffle to realign the values, which is pretty expensive. Like there's a lot of network transfer involved. If you don't care about that part and just want to apply like a custom function to every chunk in your data frame, like some adjustment from a value to, I don't know, like a logarithm or something like that, then there is a map partitions solution. Like, generally you can do help and then get the doc string. Map partitions is just map my callable to every one of my chunks without worrying about combining different chunks together. It's a very, very long doc string. We won't go through all of that now. If you look at this example of the driver pay, we get some pretty big value. That's the sum of all driver pays. And then we have a custom converter here that reduces the driver pay by a specific factor, for example, 0.5 or something like that. And this is just a small example. You could easily do this without map partitions. What map partitions now will do is will apply my function, my custom converter, to every one of our chunks of our data frame. And then give me back a new object. And so this is the initial value. If you now apply our map partitions call, you should get back 60% of that. And this is just like briefly to show that map partitions works as expected. Which should roughly be fine. You can do anything that's arbitrary, that can be arbitrarily complex with map partitions. The only difference is that it won't take all values into account. There are different solutions to achieve that, but that will be more expensive than just doing some random function on every chunk of the data. Pandas API is eager, so it will know in every step how your data looks like. If you have like 5 columns and these columns have like data type int64, for example, since Dask doesn't execute anything on the spot, it won't be aware of that at all. It will just know that, yeah, we did a selection and then we did a sum, for example. And that's why we keep track of how the data should look like, so that we can make an approximation what your next operation will be. For example, if you have a data frame with 2 columns, A and B, and you select A, and the next step selects B, we ideally want to fail early, immediately when you type in that statement. If you wouldn't keep track of the number of columns in your data frame, we couldn't do that. We could just register the column selection of B, and like if your workflow runs for an hour and the last operation fails, because of something like this is very annoying. So there's a meta attribute that keeps track of the shape of your data frame, not shape, the columns and the data types. The length is not actually known by the meta object. Yeah, this is just, if you play around with Dask, in map partitions, for example, you can provide how the new meta object looks like. And this is helpful if your converter is like complex and Dask won't be able to infer this. For this trivial example we had here, that isn't a problem because we don't add any new columns or cast detail or something like that. So now we have like 8 minutes left. We can move over to questions.
So like, sometimes when I'm dealing with like big data, an operation like draw columns is like, it's like a long time.
Okay.
I was just wondering like why in like this Dask so much like that.
You're using pandas? This is something that we will fix in 3.0. Like a lot of pandas operations make deep copies of the data. Like drop is a perfect example of that. We don't have to touch the other columns at all, but copy and use stuff in pandas is complicated. So we do a defensive copy. And this like if you only drop 1 or 50 columns, then it will copy the remaining 49, which is what takes up the time. I'll talk a little bit more about this in Friday.
2 questions. One, if I'm not using Jupyter Lab and interface but I'm on PS4, is there an equivalent extension to get all these diagnostics?
That's a very, very good question. This is just built into Jupyter Lab, but there is also a website available where you can check out the Dask dashboard. It's listed in here in the widget, and it basically shows the same things that you would see with the extension. And this is what you would use if you don't use Jupyter.
And that's also, I get something similar if I'm running it locally.
Yes,
Okay.
it's exactly the same.
Okay.
The dashboard is always the same, it just connects to different clusters. It doesn't matter if this is locally or on the cloud.
The second question was, I've since recently moved from using pandas to polars. Is that on the roadmap, making Dask like compliant with like polars API?
It might be, not at the moment. The thing that we found is that a lot of Dask users that use Dask in the cloud are actually using not that big of workers. Like they have like 16 gigabytes of memory available. And Polars doesn't offer that many speed ups compared to Pandas if you have very small chunks. Like all of our chunks in this example, like 100 megabytes. And, Dask has different bottlenecks that slow it down. I can like maybe show you one real quick. I'll just insert a couple of cells here. And we restart our client first to clean up all the data that are currently in memory. So we read the data frame. And then we do, for example, a set index. Set index sorts your data. So in a distributed setting, a sorting is very, very expensive. Let's just use a random column. The drop-off location is maybe, it's an ID, it's not unique for every thing. That's maybe something that's suitable for this. And then we can do a persist. What you will now see is like, it will trigger a lot of shuffling and network transfer. So that's what really slows us down, and just if like, I don't know, some is a little bit faster, but it help with these differences. Simply because the network transfer is what slows us down a lot. Like we are thinking about this, but like making this stuff faster has a bigger impact for most users than integrated code. Any other questions? Okay. As we can see, like the set index that is sorting the data, there are a lot of like shuffle transfers in there, which is what you use to push data to different workers. Like this is generally, if you can avoid shuffles, please do that. Thank you very much.